So normally when we are writing a query in SQL, we need to distinguish the attributes from different relations. And in the same example, in the same tables we showed before, and we design another query, we will find the name of people buying the telegraphy products. Then we need to use multiple tables, right? The first table we need to use is a person table, right? Because we need to find the name of a person. The name of the person comes from the person table only, right? And the person buys the telegraphy products. This telegraphy denotes a category, right? The category is from this product table, product.category, right? And the people is buying this product. Therefore, we also need to use the purchase, this table, right? We need to make sure the person name equals the buyer, right? And at the same time, the product also matching the name of this product, whose category is telegraphy, right? Therefore, we can design a query. So before we show the answer, you can try to do this query in the relational algebra first, and then you can check back the answer we show here in SQL. So we can write down a query like this. We have select person.name, right? We want to find the name of all the person. Beside the person table, we also need to work on the product and the purchase table at the same time. So therefore, for the from clause, we have person, comma, purchase, comma, product. We have three tables to work on. In the where clause, the first condition we have is the person.name equals to purchase.buyer. In this way, we can join the two tables together based on the name and the buyer name. Right. Besides this, we have another condition. It is purchase.product equals to product.name. In this way, we can join the purchase and the product together based on the common attribute product and product name. And we have another condition. It is product.category equals to telegraphy. Because we specify the condition in the question, right? It should be a telegraphy product. So the first two conditions, they are for the joins between two tables, between person and purchase. We join them by this name equals to buyer. This condition is for join between purchase and product. We join them based on the product name as well as product name. So these two conditions are for joins among the tables. The next one is for the pruning. We will find the products whose category are the telegraphy. So we have a tips here. Please always indicating the relation name to make sure the attributes are clear from which relation we are working on. This is very important, as later we will have more complex queries. So please specify the relation name before the attributes. So for this multi-relation in SQL queries, the semantics will be we are working on multi-relation at the same time, and we specify the conditions in the where clause, and we will indicate the relation we are working on in the from clause. And select the clause denoting the attributes we plan to projection, right? We plan to project. So therefore, when we see a query like select A1 to AK attributes from some relations like R1 to Rn with some conditions, if we have the query like this, we normally start from this relation we show in the from clause. We calculate the product among all the relations in the from clause. And then we can further apply the selection condition in the where clause to select some tuples. And finally, we do the projection of the desired attributes in the select clause to the return result. So if we translate this SQL query in the select from where statements into relational algebra, it actually equals to what? It equals to projection A1 to AK, the desired attributes, selection with some conditions in the where clause. Inside we have R1 times R2 times Rn. We calculate the product among all the relations we have in the from clause. So the select from where queries are precise in the projection, join, and select. Inside we have product or joins, and then we do the selection of the conditions, and finally we do the projection. So we can understand this query based on the relational algebra as shown here. we do a projection, selection, and product. Another way to understand semantics of this not from where clause in SQL maybe is to write down the query in another programming language like C++. If we plan to implement the same query in C++, what we need to do actually is to checking all the tuples we have in each table. So we can write down the same query as shown at the top, select from where in C++ at the bottom. We can do this query by writing down the C++ program like this, with for x1 in R1, x2 in R2, and xn in Rn. If condition hold, then we can add these data tuples into the answer. And finally, we can return the answers. It will do the same thing as select from where clauses as we show at the top. I hope it can help you understand semantics of this SQL we show in the select from where on multi-relations. So this is for multi-relation queries. For multi-relation queries, besides the case we showed before, which are really working on the different relation at the same time. And sometimes a query also need to use the two copies of the same relation for multiple times. If you still remember in the homework 2, we have one question to find the maximum value from a relation, right? So you need to use the same relation twice in the relational algebra, if you still remember. So if we write down the same query we showed before in the SQL, how can we do this? We also need to use the same relation multiple times. Here we can do a renaming of these different copies of the same relation in the from clause. So we can write down a query. For example, we plan to find a bar which didn't sell beer with the max price. Here we're working on this sales table, right? And we can do so by answering this question with a query as select s1.bar. What is s1? S1 denotes the sales table, the copy s1. We have two copies. Besides S1, we also have a sales S2. They are different copies of the same table. And here we have a where clause. In a where clause, we have to join between two copies based on the same beer names. So therefore, we have one condition to the join between them. S1.beer equals to S2.beer. So we're matching them together, right? To join them together based on the same beers. And we want to make sure this bar never share the beer with the max price. And we can do so. We have this S1 price in less than S2 price. In other words, this S1 should be smaller than some price in the sales table, right? And hence we can make sure this bar never share the beer with the max price. In this query, we use the sales table twice. We have S1, S2, and the names of two copies for the same relation. In the condition, we have the first one denoting the join condition between these two copies. The second one denoting this bar never says the beer with the max price. It is less than some price in the table, right? Okay, this is a multi-relation query based on two copies of the same relation. So I hope you can follow me on these queries, and you can practice these queries by yourself on your computer. Okay, that's it for this week, and I hope you can have a nice weekend.